Welcome back, Virtual Earth and Space Science. So we've learned a little bit about what keeps stars together and how we can describe the light that we see from them. And now we're going to talk about ways that scientists have classified stars. There are many different kinds of stars, and in order to help them understand better, astronomers have come up with a scheme for classifying stars into different types. And the way we're going to talk about today is classification by what's called spectral type. Basically, you can think of this as classifying the stars by color. It's a bit fancier than that, and we can get into a lot of details, but we're not going to because we don't have time. You can use a spectrometer to measure the spectrum of the star and very carefully look at all the different spectral lines. And so still, it's basically color information you're using to classify the stars. And for stars, color is sort of a shortcut for temperature. I think we've talked about this before. A red star is putting out red light, which is relatively low energy light, and so that star is cooler than a blue star. Blue light is much higher energy light, and the star that is blue must be a much hotter star. Now, even a cool star like a red star is still several thousand degrees hot. It's not cold, but it's just cold compared to a blue star, which can be, more like 10 or 20 or more thousand degrees hot. And so what we're talking about here are what's called main sequence stars. In the next section, we're going to learn about the stages of the life of a star. And of course, it starts out with the star forming or being born and ends with the star dying, and that can happen in all sorts of interesting and terrifying and cool ways. But in between, there's a long life, for most stars anyway, and that long normal middle part of life is called the main sequence. Our sun is currently in its main sequence, which is good for us. And so main sequence stars were originally classified using letters A, B, C, D, E, F, G. But unfortunately, as knowledge progressed, it was discovered that those letters weren't exactly in the right order if we were going to classify them by temperature and mass and size and all sorts of other things. And so the sequence that we ended up with, once we understood this situation better, is this: O, B, A, F, G, K, M, with the possible new addition of even smaller stars L and T. Alright, so this is on the left end of this scale, the stars are bluest, biggest, hottest, and brightest. And on the right end of the scale, the stars are reddest, smallest, coolest, and dimmest. And in between, they're in between. So that's what we call the spectral types for main sequence stars. Well, that wasn't enough for the people that were classifying these stars. They found some stars that were sort of between an O star and a B star. Sort of not quite as blue as an O star and not quite as red as a B star. So they came up with a finer subdivision. And so they broke each letter up into 10 numbers. So an O0 star is the very biggest, bluest, brightest, and biggest star of all in the main sequence. And then an O1 is slightly less than that, an O2 slightly less than that, all the way down to the wimpiest O star, which is still pretty hefty, an O9. And then we get into the Bs, a B0, a B1, a B2, all the way down to a B9. Then the As and the Fs and the Gs, and a G2 is the Sun. Okay, so in this classification scheme we're talking about, the Sun is a G2 main sequence star. And this subdividing would go all the way down to M9, the tiniest, reddest, dimmest, wimpiest star of all. Alright, so what is it that makes them main sequence and not something else? Because there are other kinds of stars too. There are giants and supergiants and dwarfs, which we're going to talk about soon when we learn about stellar evolution. Well, what makes a main sequence star is that it is fusing hydrogen into helium in its core. Okay, that's what our sun is doing right now. It's what all main sequence stars are doing. It's what keeps them alive and stable and shining for so long. Once the sun runs out of hydrogen, interesting and terrible things are going to happen. and it will no longer be a main sequence star. Jupiter, the planet Jupiter, was almost a star, but because it's not quite heavy enough to start fusion in its core, we can't call it a star. We could call Jupiter some kind of a dwarf failed star, something like that, but it's not quite a star. So a main sequence star has to be fusing hydrogen into helium in its core. Just to try to impress you, the biggest stars we know of, that are not main sequence stars, supergiant stars, can get up to 1,000 times the size of the Sun. Even though that's big, the readings you're going to find on the website make a point of saying that even if two supergiant stars are out there, they're not going to run into each other, usually, because the distances between stars are usually tens of thousands of times larger than even the largest of large stars. So collisions between two stars are very rare. They almost never happen. Even when thousands of stars pass by each other, they don't hit each other because, kind of like the particles in an atom, most of what's going on in there is empty space. And in our galaxy, most of the space is empty space, and the stars are very small compared to the distances between them. The very closest star to us is 4 light years away, roughly, which is about 60 million times the solar radius. So the Sun is big, but the distance to the nearest stars is even way, way bigger than that. Alright, so speaking of size, a student once sent me this PowerPoint presentation that I have since turned into a video, and it's a really cool way to see the relative sizes of the planets in our solar system, and then comparing that to the Sun, and then comparing the Sun to all sorts of different stars out there. Stars bigger than our Sun, and then some huge super whopping giant stars out there. So I think you'll enjoy it. It also has a little bit of a nice philosophical message at the end. Now this is really fascinating. It's rather dazzling to see it presented this way. Look at how big we are compared to scrawny Pluto and Mercury and Mars, and how close to the size of Venus. There's our beautiful Earth. Compared to the giant gas planets, that's nothing, that Earth. Look at how big Jupiter is, and Saturn, even Uranus and Neptune. And look how small Pluto is. And then stacking us up against the Sun, even Jupiter looks like a shrimp. Wow, the Sun is huge, right? Well, check this out. I certainly thought it was enlightening, but beyond our Sun, it's a big universe. There's the Sun. Look how it stacks up next to Sirius, a nearby star, or Pollux, or Arcturus, a giant star. But even Arcturus is tiny compared to Rigel and Aldebaran and Betelgeuse and Antares, a giant, terrifying star, the 15th brightest star in the sky, over 1,000 light years away. How big are you and the things that will upset you today? Or for that matter, the things that are important? Keep life in perspective. Pass it around to all the people you know. It might help someone get a better feel for the important things in his or her life. Hope you enjoyed that. Well, that's it for this section. I'd like you to try the online readings and questions that I've directed you to in the Blackboard assignment for this week. Good luck, and please send me questions if you don't understand. Alright, until next time.